The theory of thermodynamics is one of the most foundational concepts in physics, dealing with the principles that govern the flow and transformation of energy in physical systems. Thermodynamics plays a crucial role in nearly every scientific discipline, from chemistry to biology to engineering. It is essential for understanding the behavior of matter and energy in systems as diverse as engines, living organisms, and even the universe itself. At its core, the theory seeks to explain the relationships between heat, work, energy, and the properties of matter. The roots of thermodynamics lie in the study of heat and its relation to mechanical work. Early developments in the field were driven by the need to improve steam engines during the Industrial Revolution. Scientists and engineers began to investigate how heat could be harnessed and converted into mechanical energy, leading to the formulation of the laws of thermodynamics. The first law of thermodynamics, also known as the law of energy conservation, states that energy cannot be created or destroyed. It can only change forms. In other words, the total energy of an isolated system remains constant. This law can be mathematically expressed as delta U equals Q minus W, where delta U is the change in internal energy of a system, Q is the heat added to the system, and W is the work done by the system. This law is a restatement of the principle that energy is conserved in all physical processes, including the conversion of heat into work and vice versa. For example, when you heat a gas inside a cylinder, the gas molecules move faster, and the pressure inside the cylinder increases, which can then perform mechanical work, such as moving a piston. The second law of thermodynamics introduces the concept of entropy, which can be thought of as a measure of disorder or randomness in a system. This law states that in any energy exchange, the total entropy of an isolated system will always increase over time. In practical terms, this means that energy tends to disperse or spread out in a way that increases disorder. The second law is often phrased in terms of heat flow, stating that heat will naturally flow from regions of higher temperature to regions of lower temperature, and not the other way around, unless external work is applied. This is why ice melts in a warm room but does not spontaneously freeze. Mathematically, the second law is often expressed in terms of the increase in entropy S of a system, delta S G0, where delta S is the change in entropy. In any irreversible process, entropy increases, reflecting the tendency of energy to disperse and the universe to move toward a state of greater disorder. This law explains why processes like the burning of fuel or the operation of engines are never 100% efficient. Some energy is always lost to the environment as heat, increasing the system's overall entropy. The third law of thermodynamics addresses the behavior of systems as they approach absolute zero temperature. According to the third law, as the temperature of a system approaches absolute zero, 0K, the entropy of the system approaches a minimum value, often taken as zero for a perfect crystal. This law implies that it is impossible to reach absolute zero in a finite number of steps, making it a theoretical limit rather than a physically achievable state. The third law provides insight into the behavior of materials at very low temperatures, and is essential for understanding phenomena like superconductivity and superfluidity. The zeroth law of thermodynamics, although formulated after the first three laws, is foundational in its own right. It establishes the concept of temperature as a measurable and transitive property. The zeroth law states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. This simple yet profound principle forms the basis for the definition of temperature and is essential for the operation of thermometers. Thermodynamics has a wide range of applications in both theoretical and practical fields. In physics and chemistry, it provides the framework for understanding phase transitions, chemical reactions, and the properties of gases and liquids. In engineering, thermodynamics is fundamental to the design of heat engines, refrigerators, air conditioners, and power plants. In biological systems, thermodynamic principles govern metabolic processes, including the conversion of food into energy within cells. One of the most significant applications of thermodynamics is in the development of the Carnot engine, an idealized heat engine that operates on a reversible cycle. The efficiency of a Carnot engine is determined by the temperatures of the hot and cold reservoirs between which it operates. The Carnot efficiency provides an upper limit on the efficiency of real-world heat engines, which are always less efficient due to inevitable energy losses. Thermodynamics is also crucial to the study of cosmology. The second law of thermodynamics has been applied to the concept of the heat death of the universe, a theoretical scenario in which the universe reaches a state of maximum entropy, with all energy uniformly distributed and no work capable of being performed. This concept helps scientists understand the long-term evolution of the universe and the fate of stars and galaxies. Despite its long history and fundamental importance, thermodynamics continues to evolve. Advances in quantum mechanics have led to the development of quantum thermodynamics, which explores the thermodynamic properties of systems at microscopic scales, such as atoms and subatomic particles. These new developments have expanded our understanding of the behavior of energy and matter in the quantum realm. In summary, the theory of thermodynamics provides a comprehensive framework for understanding the behavior of energy, heat, and work in physical systems. Its 4 laws: energy conservation, entropy, absolute zero, and temperature equilibrium are essential to explaining a wide range of phenomena, from the operation of engines to the behavior of the cosmos. The principles of thermodynamics are not just theoretical. They have profound practical applications in science, technology, and our everyday lives, making it one of the most important fields of study in physics.